All right, today we're going to dive into a really cool paradox, one that's kind of at the heart of machine learning. How can you force a network to know less, to actually make it learn more? Sounds weird, right? Let's get into it.
I mean, think about it. It seems a little strange, doesn't it? Why would you go to all the trouble of building a complex neural network just to copy an image? It feels like this totally pointless exercise. But what if the real goal isn't the copy itself, but what the network is forced to learn along the way?
And that right there brings us to our main subject today, the autoencoder. Yeah, at first glance, it looks like a simple copying machine, but its real magic, its real power, is all in that journey from the input to the output.
Okay, so what is an autoencoder really? Well, it's a type of neural network that's trained to do one thing, try to copy whatever you give it. And it's basically made of two key parts. You've got an encoder, and then you've got a decoder. This image shows it perfectly. You feed the network an image, in this case a handwritten 2, and the whole goal is to spit that same 2 out the other side. Seems simple enough. But, the really interesting stuff, that all happens in the middle.
So let's look at the first half of this trip. We're talking about the encoder. Now, the encoder has a very, very specific and super important job to do. It isn't just passing the data along, it's fundamentally changing it.
See, the encoder's whole job is to compress the data. It takes that image of the 2 and it literally squeezes it down into a much smaller, much more condensed form. It's forced to find a more efficient way to hold on to that information. And that squeeze, that's where we find the big idea we're talking about today. It's a totally deliberate constraint, and it's known as the undercomplete bottleneck. So here's where we get some of the lingo. When that middle layer, the part they call the code, is smaller than the input layer, the whole thing is called an undercomplete autoencoder, which, is really just a fancy way of saying we're forcing a whole bunch of data through a tiny little opening. And that's our bottleneck, exactly. Just imagine a 5-lane highway that all of a sudden narrows down to just 1 or 2 lanes. The traffic has no choice but to squeeze through, right? It's the same thing with the data here. It can't just cruise on through. It has to compress. This comparison makes it crystal clear. Over on the left, you see the undercomplete model with that skinny middle layer. That's our bottleneck. But look at the right. That's an overcomplete model. Without that bottleneck, the network would just mindlessly memorize the input. It wouldn't learn a thing. So, okay, this brings us all the way back to our first question. Why on earth would you do this? Why intentionally create this traffic jam for your data? Well, the answer is that forcing the data through this narrow passage is exactly what forces the network to actually learn something. So let's break down the why. It's really about 2 main things. One is called dimensionality reduction. That's just making the data smaller and easier to work with. The other is feature learning, because in order to rebuild that original 2, the network is forced to learn the most important, the most critical features of the data, like the very essence of what makes a 2 look like a 2. And this quote just says it all. The network isn't just memorizing pixels anymore. It's forced to understand the deeper patterns because there's literally no room in that bottleneck for anything except the absolute most essential information. And this diagram just wraps it all up beautifully. The original input gets squeezed through that undercomplete encoder, creating this tiny, compressed representation. And then the decoder has to use only that essential information to try and reconstruct the input. It's just a really elegant and surprisingly powerful process. So if you take one thing away from this, let it be this. The bottleneck isn't some kind of limitation. It's the whole point. It is the crucial feature that transforms a dumb copying task into a really powerful learning machine. It's where less truly becomes more. And that kind of leaves us with a final thought, doesn't it? This whole thing is about finding this signal in all the noise by forcing compression. So it makes you wonder, what could you learn, not just about images or text, but about any complex problem, if you were forced to find the absolute undeniable essence of your data?